Okay, let's begin. We're going to continue with our series. Representing functions as a power series. Because I sort of already told you the main idea here, but the idea is we know a power series for something, we can figure out the power series for its integral and its derivative, provided it's absolutely continuous. We also looked at figuring out the radius on which something converges, the interval, and we can, if we use the ratio test, we can get at the same time that it's absolutely continuous on the interval, and so we can actually integrate and differentiate power series on any interval that we know is in the interval of convergence. So last time, and this is important, we found a power series for this guy. And that was, it goes from 0 to infinity of x to the n. And the idea was, we thought of that as a geometric series. This is geometric with a equals 1 and r equals x. And of course, by that same token, that means it works when your x is less than 1 in absolute values and the convergence is absolute. Which means we can find power series for the integrals and derivatives above. And generally, not just for this particular power series, but in general, if I have any power series and I'm on an interval where that power series absolutely converges, I can do this in general. And generally, for any power series. Where it converges absolutely. That said, we're going to use this guy a little bit more with a few examples. Find the power series of the following. A. Also state where they converge. So we'll stop that. This will be the last example in this section. There are going to be 4 parts. I'm going to want you to compute this guy. Power series. It's worth noting that with all the techniques that I gave you this semester, we actually can't integrate that. So trying to integrate it without power series is going to be very difficult. In fact, it's impossible. So one principle is, there are a couple ways we can find the power series for a random function. One method is if we know the power series for a similar enough function, we can pretty much kind of use algebra to finagle the function that we're considering to look like a function that we know the power series for, and then we can use that to get to the actual power series for that function. So let's see how we would do that for 1 over 3 plus x. How can you make it look as much as possible as 1 over 1 minus x? I want it to look like 1 over 1 minus something. Well, how could I make that 3 into a 1 without actually changing any values? Yeah?
Do you just like, I don't know, I'm guessing,
Yeah.
take -3 out and then do it 1 minus 1/3?
Yeah, I mean, it's regular algebra, isn't it? It's not really a trick question, it's just what algebra techniques you can use. Well, the fact that that's a 3 and you want it to be a 1, you can factor out 3. Right, so I can just come over here and pull that 3 out. I would get a 1 here, plus of course x over 3. Second of all, I want to make sure that there's a negative sign in the middle, but I have a positive sign, so what can I do here?
Make it a -3.
Make it a negative of a negative x over 3. Just throw in a double negative here, which we know means something positive. So this really is 1/3 times 1 over 1 minus x over 3. So now this kind of looks like this guy, but instead of x, I now have x over 3. So that is now this. And so now this looks like 1 over 1 minus x, where my new x is x over 3, and so I can plug this directly into a power series. This is going to be 1/3 times the series, and it goes from 0 to infinity. And instead of x to the n, I now have x over 3 to the n, minus.
Yeah. I was like,
So what happens is now, what that basically means is this, I can just distribute the power across the product, so it turns this into an alternating series. I can write like that, or I can write like x to the n over 3 to the n. Now what is going to be the radius or interval of convergence here? Now, we could jump into the ratio test here, but because I know what the original series works for, it's even easier. I don't have to go through all that computation all over again. So now we know that if 1 over 1 minus x is equal to this series x to the n, when your x is less than 1. And again, we're just going to be using a pattern here. X shows up here, x shows up here, and that guy is the bound. So it means, therefore, if I have 1 over the third, I can factor out. This is 1 minus x over 3. Then ultimately what's going to happen is, by the equivalent calculations, I will end up saying that this is going to work if that guy is less than 1 in absolute values. So I can literally just swap my x out for whatever function I've left inside, and you'll realize that basically what that means is that your x in absolute value must be less than 3. Let's multiply both sides by 3. So this means that 1 over 3 plus x is actually equal to this power series. It's the alternating series of x to the n over 3 to the n, and that will work as long as my x value is less than 3 in absolute value. So I've just found a power series for this function. And I did it by just algebraic manipulation to make it look like the power series for another function. and I can just kind of swap them out. So it's kind of like I'm using a composite function, right? I went from looking at, if I think of the original function, g of x is 1 over 1 minus x, what I just expressed f of x as is just g of minus x over 3. Right? It's like I can swap the functions, or I can plug in various x values, and this is a very cool thing to be able to do because the series and the function are the same, and I'll talk a little bit more about that. Plugging in something for the x value here is the same as plugging in something for the x value there. So ultimately, if I just figure out what that x is replaced by in some sort of algebraic simplification, then I can replace the x's everywhere in the series. And I can find a new series for that guy. And ultimately, this is what I get. So this would be the answer. Right? Which may have been a possible question. So I can say something like, for example, on the final, use a known power series to find the power series for this function. That could be a question. And this is how you do it. And if I ask for the interval of convergence, well, you just, again, piggyback on the interval of convergence for the known series and just swap in the expression that the x was replaced with. What about b? Suppose my function is 1 over 3 plus x squared. And the hint would be, how does this guy relate to this guy?
It's the whole thing squared.
Just substitute.
Yeah, but how would you get to a power series there? Remember, the square of a sum is not the sum of the squares. So to square a power series, you're like multiplying, you're like expanding to infinite polynomials. Which is, you could do it technically, but you probably don't want to.
Can't
Yeah.
square root.
No.
Could we do a partial fraction and treat it as two different power series?
No.
Oil? No.
You could FOIL and get 9 plus blah 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 and try to get factor out of 9 and try to make it look like 1 minus this. But then you'd get a whole expression here. And again, that's going to be some of your raised to the nth power. You have to multiply that out. That's not going to be nice. Could you tell me the relationship between those two? I mean, we're in a calculus class. So.
Oh, wait. Isn't that its derivative or something?
The derivative of this is the negative of that. In other words, I can think of this as the negative derivative of this. And I know the power series for that. I also know that that power series converges absolutely on this interval. So that means this is equal to negative derivative of the series I just found. Minus 1 to the n, x to the n over 3 to the n, before x is less than 3. And I can switch these two. I can bring the derivative inside. This would be minus 1 to the n plus 1, because I bring in the negative 1 and multiply this negative 1 to the n, so it now becomes negative 1 to the n plus 1. And x to the n over 3 to the n. And this I can do because of absolute convergence. We can switch the series and the derivative. Yeah.
You see down here we had the 1/3 in front of the series?
Yeah, it's supposed to
Do
be
we
there.
need to have a,
Yes, it's supposed to be there. I just forgot it.
and,
So what I can do is bring that 1/3 in.
uh,
So the 3's in the denominator will multiply, and this will be n plus 1.
So even over there in the red, that box, what, 1/3?
This was also, I also forgot. I wrote it here, but I didn't get back to it. Yeah, the 1/3 is a part. And so now what I do is I just want to differentiate this expression. And I know it looks freaky, but remember this is the derivative with respect to x, which means the n is just a constant. These guys are just constant. I'm just differentiating pretty much x to the n. And so what this becomes is n x to the n minus 1. This works for x less than 3.
So wait, why is it n plus 1?
For what?
Oh,
For what? For which part?
like at the beginning part, we just had the negative derivative, 1/3, and then everything's like n, but then right below.
Yeah, so this here is a negative 1
Uh-huh,
times negative 1 to the n. You add the powers, you get this.
uh-huh.
And then the 1/3, the 3's in the denominator multiply, so it's 3 to the 1 times 3 to the n. So you get 3 to the n plus 1,
Okay.
right? Because when you multiply things, you add their powers, so you base.
It's like you have an extra -1, you have an extra 3 that's multiplied. So you just
Okay.
add it.
So we could leave it there. There's a little bit of simplifying you can do here, where you can just sort of shift the index to make it look like n, but it's more for aesthetic reasons. It's not going to change anything. So you could stop here.
Shift
Or-
the indexes in, like move it to.
Yeah, swap all n's to n plus 1s to make that look. So it's like you're shifting how the formula works. So this would be like. But that's just for to make it look like x to the n, because you like that. Yes. And we can start this from 0. But that's not something you have to worry about. Like this will be good enough here. We're in trouble to forgot too crazy. What do you think about C?
Integral 1/3.
That was the integral of the guy that we found. So this is just the antiderivative of 1/3 plus x. X. But that's just the antiderivative of this function that we found. And because of absolute convergence, I can swap the series and the integral. So I can compute the integral of this and get the power series for that. So then that's just x to the n plus 1 divided by n plus 1. Of course, there's going to be a plus c. And again, that works on x less than 3. So what we can do is we can find that plus c. So this means that ln of 3 plus x is equal to this sum . And if I want to solve for that plus c, I just can plug in a convenient x value on both sides. Notice that if I plug in x equals 0, I end up with my c is ln 3. Yeah?
For the denominator, would you get n plus 1 times 3 to the n?
From integrating x to the n, the integral is x to the n plus 1 divided by n plus 1. Yeah, so remember the integral is with respect to the x. So all of these guys are literally just constants. So you ignore them. Just integrate the x function. So that way we can say that ln of 3 plus x, I can think of it as ln 3 plus this guy. And that works as long as we're on that interval. So if you know a power series, then if something is similar enough, we can finagle it to look like that guy and figure out a power series. Once we can figure out that power series and we know where it converges absolutely, we can actually just figure out power series for the integrals of that function or the derivatives of that function by just differentiating or integrating the power series respectively. So that's a very cool thing to do. Let's go to another example. And what I'm illustrating here, we'll be able to do it in a far more general setting, but I'm just kind of teaching you the techniques using the 1 over 1 minus x as the example. But the next example. So you see that and you might decide that, hey, well, with all these integration techniques you learn in Calc 2, I'll just try one of those. And then you'll try, oh, substitution is not going to work, by parts is not going to work. They're not going to work, none of them are going to work. And so power series provides a way to actually do things when, it's weird because you won't have an antiderivative in terms of any of the familiar functions, but it's possible to have an antiderivative in terms of an infinite sum. And what that means, when we say we can't find the antiderivative as a function, what that means is that this infinite sum we can't figure out what it converges to. But again, in a lot of contexts, that's okay. We don't need to get to the answer. We should be able to just approximate the answer to any degree of accuracy we want, and that will be good enough. So oftentimes, finding the answer as an infinite series, even though technically you don't know what it converges to, is still very useful. And so, the trick here is to realize that you would think of this as x times that. Now this guy should be starting to look familiar. What do you think we can do with that? Plus sign here. The thing I know about the form I know has a negative sign, so I just take the negative of a negative. And now that looks like the 1 over 1 minus x. So this is going to be like the integral of x times the sum of minus x to the 9 to the 10. Now this x I can multiply in, so I would have the integral of the sum of minus 1 to the n x to the 9n plus 1. And because that converges absolutely on the interval, can swap the two. 2 divided by 9n plus 2. So it's plus c. So that's what the answer would look like as a power series.
Then we would find the c again as well.
Well, we don't actually know what it's equal to, right? We know this is equal to that.
Oh, sorry, yes.
So,
Right.
so it depends. If we had a definite integral, there's
Right.
stuff we could do. But without that, we don't know. That's just a plus c as far as we're concerned. And that sort of ends this section. So it's just playing around with the series 1 over 1 minus x. But the techniques we learned about that is it's going to be very useful in the future. But what we want to do in the next section is kind of try to generalize this. What if I can't, if the thing won't look like, I can't make it look like 1 over 1 minus x? What if it's like a sine function, right? What do we do then? Like, how are you going to use algebra? What kind of magic are you going to use to turn sine of x into 1 over 1 minus x? You're not going to be able to do that. So we want to be able to apply what we learned in this section more in general. So this leads us to Taylor series, which is it's actually the last section in this syllabus. So we can probably finish everything today, and then we have 2 review sessions. So I'll try to finish this up and maybe talk a little bit about what I expect the final to look like. I didn't write it yet, but I'm getting a better picture of what it's going to look like, and I can tell you where I am right now, and I don't think it's going to change much. But if it will, I will of course inform you. So we're going to do 11.10, what's called the Taylor series. And basically what this is, it's going to be a way to find power series for arbitrary functions. One caveat though, you can't just any random function you want. There's one little catch. They must be infinitely differentiable. So you can differentiate it, then find the derivative of the derivative, then find the derivative of the derivative, then find the derivative, and you can do this forever. Once your function fulfills that criteria, you can find a power series for it. Yeah.
So I assume that this is mostly for like the trig functions.
Any function. Yeah,
Well, but
like anything that's infinitely differentiable,
Right.
but especially functions like trig functions and things like that, that we can't really maneuver to look like any other nice rational
It's
function.
like the polynomials, then you'd kind of have that covered by the other one, and then this kind of.
Yeah. So that's the catch, right? So here's how it works. You kind of figure it out in hindsight. So let's pretend that I have a function that I can write as a power series, and then I'm going to figure out what would that have to look like, right? So assume f is infinitely differentiable, and we can express it as, let's say, a power series. So I can write f of x as some infinite polynomial centered at a certain value. So I can write it to look like cn x minus x naught to the n, right? So that's the general power series formula. So it's like an infinite polynomial where x minus x naught is your variable. That's the center point. So I can write it as something like c0 plus c1 x minus x naught plus c2 x minus x naught squared plus x minus x naught cubed plus da da da. Right? So now so let's figure one thing out. So the idea is, I don't want to have to deal with an infinite number of terms, so what I'm going to do is I'm going to evaluate both sides at a certain x value. What's a convenient x value? Well, the x value that's going to kill all of these terms. If I plug in x equals x naught, all these terms go away and I'm left with c0. So what I know that is f evaluated at the center point will just give me c0. Now let's take a derivative. Now derivative of this is just derivative of polynomial. Derivative of that is 0. Derivative of this is just going to be c1 plus the derivative of that 2c2 x minus x naught plus 3c3 x minus x naught squared plus 4c4 x minus x naught cubed plus da da da. And so now what you realize is that if I evaluate the derivative at the center point, I can kill everyone else except this guy. That just gives me c1. So I can write the coefficients of the series, at least for the original function, its derivative, as that guy. Let's see if this pattern continues. F double prime, I'm going to differentiate this. Derivative of that is 0. Derivative of this is 2c2. Derivative of this is 3 times 2c3 x minus x naught plus 4 times 3 times c4 x minus x naught squared plus da da da. Basically what this means is the second derivative evaluated at x naught is 2c2. So the third derivative is just going to be 3c3. Let's check to make sure. Don't want to jump to conclusions so quickly. So basically we're going to do this until we start to see a pattern for these coefficients. If I take the triple derivative, I would get 3 times 2 times c3 plus 4 times 3 times 2 times c4 x minus x naught to the 1 plus da 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 da. Notice that here the triple prime evaluated at x naught is going to be 3 times 2 c3. Let's do one more. F to the fourth derivative. Let's make sure we can see a pattern here. So this is just a constant, that's going to die. I'm going to have 4 times 3 times 2 c4 plus 5 times 4 times 3 times 2 c5 x minus x naught 1 plus da da da. So if I say to the fourth derivative, evaluate that at x naught, I would get 4 times 3 times 2 c4. We're starting to see a pattern here.
Yeah.
Notice here, I mean, 4 times 3 times 2 times 1, sure. And this times 3 times 2 times 1, sure. So what is 4 times 3 times 2 times 1? 4 factorial. And what is 3 times 2 times 1? 3 factorial. And 2 is 2 times 1, which is 2 factorial. So now I'm starting to see a pattern. So basically what happens is this guy is telling me that the fourth derivative evaluated at the center point is going to be 4 factorial times c4. In other words, the fourth coefficient is going to be the fourth derivative evaluated at center point over 4 factorial. This similarly is going to tell me that the third coefficient is the third derivative evaluated at the center point over 3 factorial. This guy tells me that the second coefficient must be the second derivative evaluated at the point over 2 factorial. This is going to be the first derivative evaluated at the point over 1 factorial. And this guy is going to be the 0th derivative. Take the derivative, evaluate at the point over 0 factorial, which 0 factorial is 1. So it seems to me that now we have a pattern. This is a polynomial, right? It's the pattern of how when you're taking derivatives is going to be highly predictable because polynomials behave very nicely. So in general, you could say the nth coefficient will be given by the nth derivative evaluated at the center point divided by n factorial. So in general, if I have a function and the only requirement is that it is infinitely differentiable, I will be able to write out a power series for this function in a very predictable way. The coefficients of each term x to the n will be this value. And whenever we write out a series in this form, this is called the Taylor series. I.e., if f is infinitely differentiable, we may write f of x is equal to the series from n equals 0 to infinity of f to the nth derivative evaluated at x naught over n factorial times x minus x naught to the n. This is called the Taylor series of f of x about x naught, or you can often say centered at x naught. So that's a very important formula. It's the main formula for this chapter. And it gives us a way to compute power series for any function that I know how to take the derivative of repeatedly. So it's cool if it looks like 1 over 1 minus x, but even if it doesn't, that's cool too. This can deal with sine, cosine, tangent. I know how to take derivatives of all those repeatedly. Hopefully it's in a form where this, you can also see a pattern when you're computing a bunch of derivatives, and that's even nicer. Otherwise, you can just compute enough terms that will fit the approximation that you need. Yeah. There's also another version of this, but it's just pretty much centered at 0. The series, the Taylor series centered at 0. Right, that's just when you write your f of x as the sum n goes from 1 to infinity. F, the nth derivative evaluated at 0 over n factorial times x to the n. It's also commonly used. A lot of times we want to center things around the origin. So it's pretty much the same as this. I just plug in x naught equals 0. And they give this also a name. It's called the Maclaurin series. You don't have to say where it's centered, because saying Maclaurin means the center is 0. Let's do an easy example. Find the Maclaurin series for f of x equals e to the x. So good luck making that look like 1 over 1 minus x, but it doesn't matter. E to the x is easily differentiable. It's the easiest thing to differentiate. It doesn't change, right? Besides 0, it's the easiest thing to differentiate. So here's what you would do. You're just going to try to figure out a pattern. So we know we want the Maclaurin series. This means that x naught is 0. So what I'm going to do is f of x equals e to the x. This means that f evaluated at 0 is e to the 0, which is 1. Now we take the derivative. That's e to the x. If I evaluate the derivative at 0, it's 1. Take the second derivative. Well, that's e to the x. Evaluate the second derivative at 0. Well, that's 1. I think we kind of see the pattern here. It turns out that the nth derivative of this is going to be itself, which means that the nth derivative evaluated at 0 is 1. Which means Cn is going to be equal to 1 over n factorial for the Taylors, for the Maclaurin. And so I'm just going to plug in that expression into this formula. Well, into this formula. This means that my e to the x I can write as the series 1 over n factorial x to the n. N goes from infinity. We often write it like this. N goes from 0 to infinity of x to the n over n factorial. I.e., if I want to write e to the x as an infinite series, it will be 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x over 1 factorial. And that is e as an infinite series. By the way, we actually looked at this guy with the ratio test, and we found that the interval of convergence was actually infinite. It was the entire real line. So that means this guy converges absolutely on the entire real line. So e to the x is equal to this guy on the entire real line. Saw this last time. Saw that x to the n over n factorial converges absolutely on our last time. Using a similar process, we can figure out patterns for some other common functions. In Calc 2, there are 4 that you need to know. We can use the same process on sin x and cosine x are the common ones. And we now have the following.
Quick question.
Yeah.
Is it possible to generalize the e to the x power series for e to the px, where p is some constant?
Yeah. In fact, e to the f of x is just, you're going to put f of x in here. Yeah. They are the same. Now that I sort of have to justify to you, but this will actually be e to the x, and you can plug one into the other. It's not always that a Taylor series fits on top of the function is representing exactly, but in the case of these functions I'm going to mention, you it does. In the given range. So at this point we have the following. 1 over 1 minus x is equal to this series of x to the n, where n goes from 0 to infinity. That works for x less than 1. E to the x is equal to the series from n goes from 0 to infinity of x to the n over n factorial. That actually works for all x and r. Sin x, you can do this similar process. Evaluate sin x at 0, take its derivative, evaluate that at 0, take that derivative, evaluate that at 0. You'll come up with a pattern for these guys. It will end up being an alternating series. It turns out when you evaluate sin of 0, you get 0. The third derivative would be 0, the fifth derivative would be 0, and blah, blah, blah. So it turns out that all the odd powers are the ones that remain. Sine is an odd function, so that's kind of poetic how that works out. So you write the powers as that over 2n plus 1 factorial. This is 0 to infinity. By the way, this also works for all x and r. So it works on the entire real line. Cosine x. Cosine x is an even function, and as one would expect, it only works on the even powers. So powers that are double of some integer. For all x in R. Hate to say it, but you're gonna have to memorize these. It's one of those things they expect you to memorize. It's not gonna be fair if I tell you you don't have to memorize it, because then. Yeah, things like Simpson's rule and trapezoid, after you do that, no one's gonna ask you, what's the form for that again? No one's gonna ask you. But they will expect you to know what is e to the x as a power series, what is sine x as a power series. Those are very common things to ask. It is something you would be expected to know. So, yeah. So these functions you can know, and you can also be aware of. You can actually replace the x with expressions and figure things out. So if you wanted to figure out the power series for e to the minus x squared, just replace x with minus x squared. You should also be aware of the fact that you can find the power series for the integrals or derivatives of any of these guys. You can also find power series of very commonly known functions. So if you wanted to say something like tan inverse of x, how would you write that as a power series? Well, you realize that tan inverse is just 1 over 1 plus x squared, right, which is 1 over 1 minus x squared, which is going to be the sum minus x squared to the n. Right? And so you can find a bunch of things like that, right? So once you know these guys and you can finagle other people to look like them, then you can use this form of the power series and just actually swap them in. And because whenever you're on this interval, they're absolutely convergent, you can swap the integral and derivative and just find the power series for this guy by just integrating that function. So you can find power series for all kinds of functions by building on these. If you have a function that is not similar to any of these in any way, then as long as you can find a derivative, you can use the Taylor series way of finding a power series. So there are a lot of functions for which we can find power series, and it's useful when we can find them and when they actually work out very nicely, when they converge absolutely on some non-trivial interval. It's a very nice thing. And it means even if the function is so ugly that none of our rules of calculus that we've learned up to this point can work, well, all the rules of calculus work on polynomials. Right? Those are very nice functions to work with. And so if you can express something as an infinite polynomial, that's a good thing to be able to do. So I'll give you something to work on. So a problem like this type will be on the final in the second part. There's going to be a compulsory section and an optional section. This will be in the optional section. A. Find a power series. Well, specifically, I'm going to say a Maclaurin series. For sine 2x squared. Now you could build that from scratch by finding all derivatives, evaluating at the points, and figuring out a pattern, but because we know what this guy is, that's not going to be a problem. So that should be like a one-step process. B. estimate the integral from 0 to 1 over 10 of sine of 2x squared dx as a sum of 3 fractions. For emphasis here, I'm going to use which means the idea is you're going to write this as a power series, integrate the power series, plug in the limits, and you'll get the answer as an infinite series. Take the first 3 terms. Z. Find an upper bound for the error, i.e., how good is the approximation above? Tell me how far you are from the actual answer at most. So if I compute this integral and I only take the first 3 terms, I'll get some answer. Compared to the actual answer for the entire integral, how good of an answer is that? How far am I from the actual answer? What is the approximation? By the way, impossible to integrate. There is no function for which, if we take the derivative of it using the derivative rules that we have, we will get sine of 2x squared as an answer. It doesn't have a general antiderivative. So now we have options. We can stop here and continue tomorrow, or we can take like 15-20 more minutes and finish everything and then just start, not tomorrow, Monday. We're meeting again on Monday and Wednesday. So we can stay here a few more minutes and finish literally everything that I want to talk about, and then it's just review on Monday and Wednesday. Or you guys can leave now, try this on your own, and then we finish up on Monday and then start review. What do you guys want to do?
Has anybody got anywhere to be?
Yeah. It's
Let's finish those.
I mean, I'm down to finish it so we don't kind of get stale on it.
Yeah, so let's actually do this example then. I'll talk about a few other things that are kind of cool, and we will wrap up. And then I'll tell you about the remainder term for Taylor series, like how we can find a bound in general. The trick to this one is that that's going to end up being an alternating series, and so we can use the alternating series approximation there, which is pretty easy to apply. But in general, if you didn't get an alternating series, there is hope. And so I would just mention a little bit about that. But I wouldn't test you on it, but I'll just mention it for your general edification. Okay, so if something like that showed up in the final, this is what the solution would look like. Or the solution I would expect you to do. It's not the only way to skin the cat, but so you could just brute force develop this from scratch by doing the formula, the nth derivative evaluated at 0 over n factorial, and try to find a pattern for that and write it down. But it's much easier to just use the fact that we know what sine is. Since sine x is the series minus 1 to the n x to the 2n plus 1 over 2n plus 1 factorial, this means that sine of 2x squared is going to be, just replace 2x squared with the x. Trying to emphasize what I'm doing here. Just literally evaluating the function, finding a composite function essentially. can write this down a little nicer. This is going to be 2 to the 2n plus 1 times x to the 4n plus 2. Remember this, with respect to x, this guy is just a constant, so that's part A. Part B, let's estimate that integral. So the integral from this guy is just going to be the integral of this series. Which is going to be, well, that's just going to be the series of the integral because we have absolute convergence here. And you can actually test that. This is similar to x over a factorial, so you can expect that it's going to converge everywhere. So now remember, all of this is just a constant with respect to x, so I'm really only integrating this. So I'm going to do the power rule for integrals, add 1 to the power, divide by the new power. So this is going to be the sum of minus 1 to the n, 2 to the n, 2 to the 2n plus 1 times x to the 4n plus 3 over 4n plus 3, and there's a 2n plus 1 factorial. And it is a definite integral, so plug in 0, 1, 10. So that's going to be over 10 to the 4n plus 3 over 2n plus 1 factorial 4n plus 3. When you plug in 0, you don't. So now it says to estimate it as a sum of 3 fractions. So what I'm going to do is I'm just going to evaluate this series for n equals 0, 1, and 2. So here now we're going to say this is approximately, if I plug in n equals 0, what do I get? I get 2 times 1/10 to the 3rd over 3. So that was my n equals 0 term. I'm going to plug in n equals 1. And I will have a minus sign. Cubed times 1 over 10 when n equals 1, so that's 7 over 3 factorial times 7 plus plug in n equals 2, and this will be a plus sign, so that would be 2 to the 5th times 1/10 the 11th over 5 factorial times 11. And that's my approximation. This integral is approximately that number. And part C. Since the above is alternating, we can use the alternating series approximation. So the error, I can find an upper bound for that error. It will be at most, do you remember what that theorem says? It'll be at most less than or equal to the fourth term. The size of the fourth term. So that's going to be when I plug in n equals 3. So in an alternating series, a term tells you how good the approximation of all previous terms is. So if I want to find how good is the approximation of the first 3 terms, the magnitude of the fourth term tells me. So if I plug in n equals 3 here, and I'm finding the magnitude, it will be minus 1 times, plug in n equals 3, 2 times 3 is 6, that's the 7th, times 1/10. Plug in n equals 3 here, that's 12 plus 3, that's 15, over 7 factorial times 15. Can you guys tell me what that is as a decimal? I'm curious. That would be the answer. You could leave it like that, but I'm curious to see how good that is. You can ignore the negative sign. 2 to the 7th times 0.1 to the 15th power divided by parentheses 7 factorial times 15 close parentheses. Really? Did you get this?
That's what I got on board. Yeah, that's what I got on board.
So you see how good that is?
It's pretty good approximation.
to 18 decimal places. From the actual answer, this is 0.0000017 zeros 169 away from the actual answer. I think that's good enough. At that point, we don't need a higher precision than that. So the fact that I couldn't actually integrate this function, I don't care. Like, I have enough to know what the integral between, what the area under that curve is. I can know it up to 18 decimal places just by taking 3 terms. So this actually converges very fast. Exponentials converge even faster.
You want the fractional result because it's 590 quadrillion over 590 quadrillion.
Yeah, that's pretty good. Yeah. Yeah, so there will be a problem like this, where I'm going to give you some function. It's going to be similar to a function that you already know the power series for, and I'm going to ask you to find the power series for that, use it to approximate a definite integral to some number of terms. You just find those number of terms, and I'm going to ask you, how good is this approximation? And you're going to tell me, oh, I used the alternating series approximation theorem to figure this out. And this is similar to what the answer to the bonus would have been in the last test, where I told you e to the minus x squared, approximate this, and you would have done the same thing, except you would have used x to the n over n factorial, plug in minus x squared for the x in that, and then you could do this. It will be less algebra than this one, because the e to the x is a much nicer power series. It's very concise. way. The error term for a general Taylor series is called the remainder term, and it's denoted by R sub n x, where you can think of it as a series on its own that has n terms. So basically, if you write the idea here is f of x, you start to write it out as a series, like a0 plus a1x plus a2x squared plus da da da. Let's say at some point you add up a finite number of terms, that's the Taylor series to n terms. Plus you have the rest of the terms over here. Those guys continuing off to infinity, that's called Rn. Right? So that's the error term. That's the difference in approximation of some finite. If you cut off the Taylor series at a certain point, what's left over is called the remainder term. Now, you might want to know, when can you trust that a power series approximates its function accurately? Well, pretty much equivalently. Right? So the idea is f of x is its Taylor series if the limit as n approaches infinity of this remainder term equals 0. Otherwise, the Taylor series can at best be thought of an approximation to the function, kind of in the way that a tangent line is approximation to a function back in Calc 1. We know it works good in a very small region, but when you zoom out, it goes to crap. Right? However, if this is true, if we could somehow find a formula for this function and it goes to 0, meaning the more terms we have, the difference between the function and the series is nothing. It's just, this series will essentially be the function, and you can interchange them at will at any point and it won't make a difference. Right? That's not always true. It's only true when this is the case. There are many versions for that, the formula that would approximate this guy. But most common, especially at like in the elementary calculus circles, is this version. It actually looks like the n plus first term. It's actually very similar to the alternating series approximation. The most common is r of x is equal to n plus first derivative evaluated at some number, or n plus 1 factorial times x times x naught, where this guy is some number. So you will be able to get an upper bound to this guy, some number between x and x naught. And so the idea is, you just want to find the best approximation. Basically what you do is you just make sure that this guy never, no matter what number you pick in this interval, just pick a number where this is always less than or equal to that. So if f to the n plus 1 of this guy is less than or equal to some constant b on the whole interval. And b is chosen to be as small as you can possibly get it. Then we can always say that the magnitude of the remainder term will be less than or equal to b times and this is called Taylor's inequality. And for it to work, the derivative must be continuous. Because blowing off to infinity at some point is going to mess with that guy or being undefined. So if you can find a general formula for the n plus first derivative, and you can know that there is some number where that's always going to be smaller than or equal to, then it turns out that your remainder term is this guy, and so you can say f is its Taylor series if the limit of b, which at this point is just going to be a constant, x minus x naught to the n plus 1 over n plus 1 factorial is 0. Otherwise, your Taylor series is just a good approximation in a very small area. But it's pretty much exactly the same as the function if your remainder term goes off to 0, and this is one of the most common ways to express that formula. Let's look at a few other uses. So I won't test you on that, I'm just kind of describing something. Might be useful. I'll list some of these, I won't do all of them. Some of them. You can use them to figure out limits. You can also do things like show, you can write ln2, even though I think I did something similar for this. Let's see what for that. You can write ln as an infinite sum. Minus 1 as an infinite sum. can write so that's for those students who like distributing radicals across sums and thinking that that's just x plus 1. It's not. You could actually write it as a sum of terms. Turns out you'll need an infinite number of terms to do it though. So you might as well just not mess with a sum under a radical. But the idea is, of course, we can just find the Taylor series for this. Evaluate at a certain point, find the derivative, evaluate it, find derivative, evaluate it, find derivative, evaluate it, construct a pattern, and you can just... So it's an alternative to like the generalized binomial theorem.
Is that an infinite differentiable function? I think it is.
Yeah, as long as you're in the domain. Yeah, you can just keep using the chain rule and then you have to use the chain and the product. Yeah,
They're all halves.
but in theory. But if you look at something like this, I'll show you in principle how you go about something like this. So if you're looking at something like the limit as x goes to 0 of sine x minus x over x cubed, you can probably try L'Hopital's rule, but I just wanted to show you with series. You can realize that the sine you can write as a series. This is just x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus da da da. The x would cancel the x. And so now what you realize is that this is just a sum of terms, and it's going to look like this guy plus x squared over 5 factorial minus x to the 4th over 7 factorial plus the next one will be minus 6 over 9 factorial minus. So obviously when you plug in x equals 0, the answer is just minus 1 9. Or you can do L'Hopital's rule like 3 times. Right? But seeing right away that, oh, the sine function, the first term in that is an x, that's going to kill that x. The second term is going to be an x cubed, which divides into that. Everyone else is going to go to 0. That's going to be my limit. And you can do that with like literally all of these. So I write this out as a series, expand the x, write this as a series. It's going to kill the 1, the x's will cancel, and you can actually find it. This I believe I showed you last time. So the idea was we used, or you can use the power series. I would use, to get rid of the minus sign, power series for 1 over 1 plus x. You'll get an alternating series, and because you think of this as sum of minus 1 to the n, x to the n, and then that means you can find the ln 1 plus x by just integrating this guy. You won't have to worry about any sign changes here, and so this would be it goes from 0 to infinity of minus 1 to the n, x to the n plus 1, or n plus 1. And this, of course, works when your x is less than 1 in absolute values. So this gives us that your ln of 1 plus x is going to be equal to x minus x x cubed over 3 plus x plugged in n equals 0, plug in n equals 1, plug in n equals 2, plug in n equals 3, plug in n equals 4. And so now you just plug in x equals 1. You can test this, but I think it converges on the
Question?
Yeah.
Would that be negative 1/6 on the limit of the sign function? Is it factorial?
3 factorial is 6.
I wasn't sure if there's something else being added or something.
For some reason, I thought 3 squared when I said.
Yeah.
Yeah, but these are just some nice things you can do. But more than likely, the question I would ask you is one like what we did with the integral. So give you some function, write it as a power series, use that power series to approximate an integral, tell me how good your approximation is. Yeah. So in terms of, but you can try some of these, it'll be fun. Now, I might put a miscellaneous problem in the bonus section where I ask you some random questions like these. Hey, can you compute this limit using a power series? Can you do this using a power series? But that would be nice. In terms of, so this is not completely set in stone, but it's pretty much. I don't think I would change much more than this, but if you want to start studying something over the weekend so that when we meet on Monday we have some substance to talk about, this will be a pretty good place to start. So here's what you can expect. We'll have to complete 8 to 9 questions. I'm thinking 9, but if the problems are too tedious when I write them, I'll probably make you do 8. There'll be 2 sections. So there will be a part 1, which is compulsory. There'll be a part 2, where you choose from options. And so of course part 1 will be where I throw all the guys in where I would expect you as a Calc 2 student to know these things, and so it's you have to know these things. So part 1. So in part 1 I'm going to ask you the typical thing, differentiate a bunch of functions using the derivative rules that we learned in this class. And of course integrate several functions. Right, you'll have to use various integration techniques. It might be you have to do a substitution or by parts or partial fractions or whatever, and the derivatives of exponentials and all that stuff. I'm going to ask you about convergence test. Approximate number, I'm thinking of 4 problems here, 3 problems here. Like A, B, C, D, A, B, C, D, A, B, C. And interval of convergence, so just remember that's using the ratio test and solving for the inequality, as well as being able to compute an improper integral. And basically dealing with the parametric curves, that's fine dy dx and dx dy. Dy dx in the second derivative. As well as probably the arc length formula for parametric curves, that'll come in the next semester. So that's the one where it's just, it's x prime squared plus y prime squared. So there's an arc length formula for if your function looks like y equals f of x, it's 1 plus f prime squared. If your x is equal to x of t, y is equal to y of t, that's the formula. Oh, it might give you a limits problem. All right, where you have to use L'Hopital's rule. So I expect these to be roughly short. The point is not to be tedious. The point is to, can you apply different techniques at different times? If you see what technique to use, it won't be difficult. I'm not going to make it computationally difficult for no reason. So those are just some options. So these are kind of things that you want to make sure that you know. In part 2, so in part 2, it's going to be something like, you're going to choose 3 to 4. And so I'm going to talk about work, arc length. Power series to approximate integrals. Approximate integrals as a topic, that means like I'm talking about the Simpson's rule, trapezoid rule, etc. Exponential growth and decay. Here between curves. Sketching and comment section. The form partial fraction decom. So I think, and that just means I'm going to give you this huge thing, write out the partial fraction form, but you don't have to solve for the coefficients. Whereas if I give you a problem here where you might need partial fractions, it'll probably be the one where you can use the shortcut, cover things up and plug the numbers. It should be short. Once you realize that it's a partial fraction, it shouldn't be too difficult to actually work it out. So currently this is the idea I have in my head of how the final might look. As soon as if there are any changes, as soon as I make them, I will inform you guys. I'll type something up on the page.
Is there going to be a review, like, other than our review classes, like an actual practice problem review? Or
Like a practice? No.
No. So
I mean, the next 2 classes we might do some practice problems, especially if there's some issues. What you guys can do is, by Sunday, if there are any topics that you really are having trouble with over the weekend, we can go over that. And I'll use problems like the kind I would write on a form, and we'll talk about it.